let's start with iterators. Iterators are objects which point to a specific location in a C++ STL container. And iterators suppose reusability of code as they can be used to access elements of any container. We'll learn more about iterators in the further STL containers like vectors, stacks, queues, and all, and then you'll be able to understand better. Let's see the most common iterators which are used for vectors and most of the other containers. The most common ones are begin and end. Begin is a function which returns an iterator pointing to the first element of the vector, and end is a function which returns an iterator pointing to the theoretical element that follows the last element in the vector. It does not point to the last element of the vector. It points to a theoretical element just after the last element in the vector. And similarly, rbegin and rend are the opposite. Rbegin returns a reverse iterator pointing to the last element in the vector, and it moves from the last element to the first element. We'll see all this in an example. They'll show you how to use all this. And rend returns a reverse iterator pointing to the theoretical element preceding the first element in the vector. Just like how end points to the theoretical element which follows the last element in the vector, rend points to a theoretical element which just precedes the first element in the vector. You need not worry about all this right now. As I explain vectors and other containers, it'll be more clear to you because I'll show you the examples also. So let's move on to vectors. Vectors are basically arrays, but more powerful than arrays. They are dynamic arrays, and they can resize them. They can resize themselves during the operations. So they're basically dynamic arrays. You can think of them as dynamic arrays. Let's see some important functions on vectors. The first function is size. Size returns the, as you would have guessed, it returns the number of elements present in the vector. Pushback is used to push the elements into vector from the back. Okay, so this is important. Pushback pushes elements into vector from the back, and popback removes elements from a vector again from the back. So let's see some examples. So I've written the code here. This is how you initialize a vector, and then the data type and the vector name. Here I've pushed these elements into the vector using pushback function as I've explained. First I've pushed 8, then 10, then 15, then 9, then 6. Okay, so there's another function empty. Empty returns whether the container is empty or not. It returns true if the container is empty, and it returns false if the container is not empty. So right now, after all this, the container is not empty. So I've written a if condition. If the vector is not empty, then I'm printing the size of the vector using the size function. And if it was empty, the output would have been that the vector vec is empty. So right now it's not empty. And if I run this, as you can see, the size of the vector is equal to 5 is being printed because I had pushed 5 elements, and vec.size returns the number of elements in the vector. Let's also look at popback. Or rather, if I would have not inserted any elements in the vector. So right now the vector is empty, and now if I run it, it should print that the vector vec is empty. So that is how the empty function works. Now let's look at popback. Okay, so after pushing these 5 elements and running this, I am popping one element from the back. Okay, popback is a function which is used to do that. And after that, again, I'm printing the size of vector v. So now it should print 4 because one element has been popped from behind. So first it was 5, and then after popback, it has become 4. So the next two functions are front and back. Front returns the first element of the vector and back returns the last element of the vector. So let's see what it outputs. And it's saying the front element is 8 because we had pushed 8 first. And then the last element is 9 because there's 8, 10, 15, 9, and 6. And here we have done pop back, so 6 was removed. So now 9 is the last element. So that's why front returns 8 and back returns 9. Now let's see how to traverse a vector. You can traverse a vector using a simple for loop from I is equal to 0 to I is less than the size of the vector. And you can access vector elements just like how you can access elements in an array. So if you write the vector name and then in square brackets, if you write the position, you'll get the element present at that position. It's just like an array. So let's see how you can traverse an array. I mean, how you can traverse through a vector. So yeah, in a for loop from I is equal to 0 to I is less than vec dot size, I've just outputted I and then vec of I. So it prints the position and the element at that position. So 0, 8, 1, 10, 2, 15, 3, 9, and 4, 6. This is the most simple way to traverse through a vector. And let's now I'll show you how to use iterators, which I had explained before. So iterators are basically an object which point to a location in a container, and this is how you declare an iterator. This is how you declare an iterator. For a vector, you just write vector and then the data type and the two colons followed by iterator, and then here PTR is the name of the iterator. You can create any iterator like this. Instead of a vector, it can be an iterator for a set also, or for a map, or any other STL container. And here the data type can also be anything. But for this example, I've created an iterator of type vector int because that is what I'm showing here also. So now I've created a iterator of type vector int. And you can traverse a vector also using an iterator. You can start the iterator from, you can first initialize it to vec.begin. So as you can see here, begin is a function which returns an iterator pointing to the first element in the vector. So now PTR will be pointing to the first element of the vector, and I'm doing PTR plus plus until PTR is less than vec.end. So vec.end returns an iterator pointing to the theoretical element that is just after the last element of the vector. So this will go on until the last element of the vector. The for loop will run from the first element to the last element of the vector, and you can print the value present in that location by using the star operation. So that's why I've written star PTR. Let's see the output. And yeah, so that is the output: 8, 10, 15, 9, and 6. So this is another way you can traverse through a vector using an iterator. So now there's another thing in C++ which is called range-based loops. Instead of the common syntax that you would know for a for loop, starting like the declaration and then the condition and then the increment or decrement or any other operation that you write, you can also write a for loop with this syntax. These are known as range-based for loops. So you write for and then the range declaration and the range expression. For example, if you have an array of size 4 elements, so this is how you can write a range-based for loop. You just write for int, the data type of the array, and any variable name, colon, the array name. And you can do this for vectors, vectors, sets, maps, any of these things. So here also, this is another way you can traverse through a vector. For int a colon the vector name, C out a. Let's see. How? So again, all the elements of the vector have been printed. There's okay. So as I had mentioned earlier, this is one way to create an iterator, right? And for reverse iterators, the syntax would be different. So for reverse iterators, you would have to write reverse iterator IT, or if you want to create an iterator for a set or a map, then you would have to write set int iterator and then the iterator name. So instead of remembering all these different syntaxes for different containers and data types, C++ has a very powerful keyword called auto. You can just remove this whole thing and write auto here. Auto, but yeah, you'll have to give it a value also. Like you'll have to assign it a value while you're declaring it. So what auto does is it automatically detects what type of iterator or what type of value this is, and it automatically assigns this variable to that data type. So now you can write auto PTR is equal to anything here. You can write a iterator which belongs to a set or a iterator which is of type vector or a reverse iterator or anything, and you can just write auto for all of these. So from now onwards, I'll be using only the auto keyword. I won't be writing the whole syntax for an iterator. And so here also I've traversed through a vector using the auto keyword. It is the same thing as before. It's just the same as this one, which I'd shown before, but instead of writing the whole syntax for an iterator, I've used auto here. So for auto, PTR is equal to vec.begin, PTR is not equal to vec.end, PTR plus plus. It's the same thing. It starts from the beginning position and it goes up to the last element of the vector. So again, it prints all the elements of the vector. Okay. And so the other two functions which I was talking about is rbegin and rend. This is a reverse iterator. Uh, rbegin returns the reverse iterator pointing to the last element of the vector, and a reverse iterator moves from the last element to the first element of any container of a vector or a set or whatever we're using. And rend is the theoretical, it points to the theoretical element just before the first element of the vector. So what I've done here is I've started from vec.rbegin. Rbegin means this is a reverse iterator, and right now it's pointing to the last element of the vector. And when I increment this pointer, it will move from the last element towards the first element because it's a reverse iterator. And I'm going till rend, which is present just before the first element. So this is why this for loop will run from the last element to the first element. And as you can see, the elements have been outputted in the reverse from the last element to the first element, 6, 9, 15, 10, and 8. So this was about rbegin and rend. And C++ also has a sort function. You can just, for sorting a vector, you can write sort, and then if you want to sort it in the ascending order, you can write sort from begin to end. So this is how it has been sorted in an ascending order. But I mean, sort by default sorts it in the ascending order. And here I'd passed an iterator from the beginning till the end. Now, if I pass reverse iterators from R begin to R end, then also it will sort in the ascending order only. But since it is from the last element to the first element, and if we print it from the left to right, it will be as if it has been sorted in the descending order. So if I pass R begin and R end as the arguments, it will print the elements from largest to smallest. So these were all the major operations and functions that you'll be using on a vector. And you would have kind of understood more about iterators also. If you have not understood about iterators, you need not worry because it'll be used in sets and maps too. And I'll be showing examples there as well. So this was about vectors. Let's move on to the next STL container, which is called stack. It is a LIFO type of container, which means last in, first out. Elements in a stack are pushed on top of the topmost element, and if you want to pop an element, if you want to remove an element from a stack, then the topmost element is removed first. So that is why it is last in, first out. Whichever is on the top of the stack is removed first. So that is a LIFO. And here again, the functions are pretty similar. Empty and size are the same as we have seen for vectors. Empty returns whether the stack is empty or not, and size returns the size of the stack. Top returns a reference to the topmost element of the stack. And as there was push back and pop back in vectors, here there's push and pop. Push pushes an element to the top of the stack, and pop deletes the topmost element of the stack because it follows LIFO. And let's see all these operations also. So here I've declared a stack. This is how you declare a stack, and then the data type, and this is the variable name. And I'm using the function empty. Empty returns true if the stack is empty, and it returns false if the stack is not empty. So this is a simple if else thing that I've written here. It prints stack is empty because I've just declared the stack here, and I've not pushed anything into the stack yet. So right now it is empty. Now if I push two elements, if I push 5 and then 8, so first 5 will be in the stack, and then on top of that 8 will be pushed. So now if I want to check how the size function works, I can just see out stk.size. This will give me the size of the stack. Pretty like self-explanatory. So size of the stack is 2. This returns 2. And the empty function. Okay, so this is how you traverse through a stack. You have to continuously, like in a while loop, you have to print the top element, and then you have to pop it, and you have to keep doing this until the stack is empty. So this is how you can see all the elements of the stack. So let's run this and see. So it prints 8 and 5. Since 5 was inserted first and then 8 was pushed on top of it, so when you run this loop, first stk.top will have 8, and that's why it prints 8, and then it is popped. So now only 5 is remaining in the stack. And again, this condition is true because the stack is still not empty. And now 5 is printed, and then 5 is also popped. Now the stack is empty, so it'll exit the while loop. So this is how you can traverse through a stack and like print all its elements or perform any operation. So we have seen empty, size, top, push, and pop. So we have seen all the operations of the stack. These are the only major operations you'll need for a stack. Let's move on to the next container. It's called a queue. It follows FIFO, which is first in, first out. the earliest element which was inserted into the queue will be deleted first, and elements are again inserted at the back or the end of the queue, but are deleted from the front. So this is the difference between a stack and a queue. Stack follows LIFO and queue follows FIFO. And here again, the functions are pretty much similar to what we have seen for vectors and stacks. Empty and size are again the same. Front returns a reference to the first element of the queue, and back returns a reference to the element present at the end of the queue. Push adds an element, push, and you'll have to pass an argument in push, and that element will be added at the end of the queue, and pop deletes the first element of the queue because it follows FIFO. And let's have a quick look at all these functions. So I've declared a queue here, you have to write queue and then the data type and whatever variable name you want to give for the queue. And again, the empty function is the same here. It should return empty because right now I've not pushed anything into the queue. So the queue is empty. And now I've pushed 5, 8, and 3. So first, 5 is first in the queue, and then behind 5, 8 is pushed, and then behind 8, 3 is pushed. So in the queue, in the front, there's 5, and then there's 8, and then at the end, there's 3. So let's see all these three functions at the same time. Q.size, it returns the size of the queue. So that should be 3 because there are 3 elements in the queue. And Q.front should return 5 because that is at the front of the queue. And Q.back should return 3 because that is at the end of the queue. So let's see if that is the output. So yeah, the size of the queue is 3 and the first element is 5 and the last element is 3. And just like in a stack, we can traverse through all the elements of queue here in the same way as in a stack. You can print the front element and then pop it. So 583. First 5 is printed and then it is popped. So now 8 is at the front. So 8 is printed and then it is popped, and then the queue only has 3. So 3 is printed and then it is popped, and then after this, the queue becomes empty and it breaks out of the while loop. So these are the simple functions which you can use in a queue. Let's move on to the next STL container, which is called sets. And sets from now, it'll be like a little different from what we have seen in vector stacks and queues. Sets are a type of associative container in which each element has to be unique. This is important. Each element in a set is unique because the value of the element identifies it. And the values in a set are stored in a specific order. We'll see what that is soon. Here again, empty and size are the same functions as we've seen before. Insert function inserts an element into the set. Begin and end are again the same iterator functions, which returns an element to the first element, and end returns an element, it returns an iterator to the theoretical element that follows the last element of the set. And here there are 3 important functions that you need to know: find, lower bound, and upper bound. Find is used to it is usually used to check if an element is present in a set or not. It returns an iterator to the element which has been passed as an argument, and if it is not found, it returns s.end. And the time complexity of this is O of log n. Then there's another function, lower bound, which returns an iterator. Okay, we'll see these two functions after we have tried out all this. So I've created a set named st, and I've inserted all these elements into the set 4, 8, 3, 10, 12. Okay, so again, this is one way of iterating through the set using the set int iterator, or you can also use the auto keyword which I've already mentioned above. Here I've created an iterator of type set int and its name is itr, and I'm running a for loop from st.begin till sg.end, and I'm printing all the values. So by default, when we create a set of some data type, it stores all the elements in ascending order of the data type. So here it doesn't matter in which order I've inserted the elements into the set, it will be stored in the ascending order automatically. And we can see this by printing all the elements of the set from first to last. Yeah. So as you can see, there's 1, 3, 4, 8, 10, 12. It has been sorted in the ascending order on its own. So that is the special thing about sets. The elements and one more thing is that the elements are unique. So if I insert 4 again here, I've inserted in the beginning also, but if I insert it again here, there'll still be only 1 4 in the set because the elements are unique. Elements have to be unique. So what a set does is it will first check if 4 is already present in the set or not, and if it is already present, then it won't insert it. And instead of using okay, let's see the erase function also. You can erase an element. You can erase an element using the erase function. And in the erase function, you have to pass an iterator of the position which you want to erase. And you can get an iterator using the find function. So what st.find of 10 will do is it will return an iterator which points to the location where 10 is present. And then we are performing the erase function on that iterator. So by this method, 10 will be erased. Let's okay, this time instead of using this whole syntax, we can also do it using the auto keyword, which I've mentioned before also. So now if we print all the elements, 10 should not be present because we have erased it using this line. So you can see the output here does not have 10. So this is a good way to erase it, but actually you should also have an if and else statement to first check if 10 exists or not in the first place. Otherwise, this will return st.end, and you might get an error if you try to erase st.end. But okay, so this was about find and erase, and then so the next two important functions are lower bound and upper bound. The lower bound function returns an iterator to the first element. I mean, you have to pass an argument in lower bound, an element, and it returns an iterator to the first element which is greater than equal to the argument passed. And it returns s.end if it is not found. Upper bound is the same thing except it should be strictly greater than x. Upper bound returns an iterator to the first element which is strictly greater than x. And if it is not found, it returns s.end. And the time complexity for both of these functions is O of log n. So let's check it using an example. Here I've created two iterators using the auto keyword. Auto it1 is equal to st.lower bound of 3 and it2 is upper bound of 3. And here I've written an if-else condition for lower bound. If it is equal to st.n, I mean, if it is not equal to st.n, that means a lower bound has been found, and I'm printing that lower bound using star it. And if it is equal to st.n, that means there no lower bound for 3 has been found, and 3 is larger than the greatest element of the set. And I've written a similar if else statement for the upper bound also. If an upper bound is found, I'm printing the upper bound. And if an upper bound is not found, then I'm printing that element is larger than the greatest element of the set. Is it's greater than or equal to than the greatest element in the set. So now, what's going to be the output of this whole thing? So we need to check the output of this. You can write it in the chat actually. You can write in the chat what do you think is going to be the output when I execute this part. The elements of the set are here on the output 1, 3, 4, 8, 10, 12. And if I try to see the lower bound of 3 and upper bound of 3 and I print it, so what is going to be the outputs? You can write it in the chat. You guys have chat access, right? Please show the opposite. Yeah. So the elements of the in this set are 1, 3, 4, 8, 10, and 12. And this is what I want to output. Lower bound of 3 and upper bound of 3. This is for the lower bound part, and this is for the upper bound part. So what's going to be the output for lower bound and for upper bound? That is my question. Lower bound, people are saying lower bound is 3 and upper bound is 4. Okay. Sumit is saying 3 and 4. Abhavya is saying lower bound 3. Akash is saying 3 and 4. Abhishek 3 and 4. Abhavya upper bound 4. Hmm. Okay, so all of you have written the correct answer. So the lower bound of 3 is 3 and upper bound of 3 is 4. Lower bound of 3 is 3 because the smallest element which is greater than or equal to 3 is 3. And upper bound of 3 is 4 because the smallest element in the set which is strictly greater than 3 is 4. So now if I try out lower bound of, what if I try out lower bound of 12 and upper bound of 12? Or wait, let's say lower bound of 6 and upper bound of 12. What would be the output now? Lower bound of 6 and upper bound of 12. Akash is saying 8 and S dot end. Abhishek is saying 8 and 12. Nimish is saying 8 and 12. So, okay, for lower bound, everyone is saying 8. Okay, for upper bound, One is saying st.end, and one is and a few people are saying 12. So what is it? st.end or 12? These are the elements. Upper bound returns like if you pass an argument, then the smallest element which is greater than this element. And if it is not found, then it returns st.end. So Akash was right. It returns st.end because there is no element strictly greater than 12 in the set. And this is the output which we had written in the else condition, and that's why that is printed. So the upper bound of 12 is not 12, it is st.end because there is no element which is strictly greater than 12 present in the set. So I hope that's clear to all the people who are saying 12 as the upper bound. So these were the main functions. And yeah, there's another modification that you can make here. If you write it in this syntax, then it will be stored in the descending order instead of ascending order. You can just write greater int here. We can print it and see. So as you can see, when we print it, it's printed in the descending order. So you can just like keep this in mind. Yeah. So now let's move on to the next. Yeah, this is the same thing. You can use the auto keyword, and yeah, there's another like even shorter way to traverse through all the elements. You need not even write this whole for loop syntax here. I talked about range-based loops earlier, right? So you can just write for auto it and then range st, and then you can just see out it. So you can just write this much to traverse through a set or even through any other thing like a map or vector. So this is how you can make good use of range-based for loops in C++ and the auto keyword at the same time. There's another container which is like unordered set, and it stores elements in an unsorted order, but you can read about it on your own later. It's out of the scope of this workshop, but usually like it's not recommended to use unordered set. But just for your information, you can also write unordered set int, and then that will store the elements in an unsorted order. Let's move on to the next STL container, which is called maps. And these are also associative containers that store elements in a mapped fashion. Each element has a key value and a mapped value. No two mapped values can have the same key. And yeah, another special thing about maps is just like how in sets all the elements were unique and sorted, in maps all the key values are unique and sorted. We'll see examples on that soon. And here again, begin and end are the same uh, function which return iterators. Size is again the same as we've seen before. Empty is again the same. There's another function called insert. Okay, so there are two ways to insert elements into a map. Okay, first of all, you can declare a map like this. This is the data type of the key value, and this is the data type of the mapped value. It can be anything. It can be int string also or string int. But right now for this example, I'm using int and int. The key value is also of type int and the mapped value is also of type int. And there are two ways you can insert elements into a map. One is using the insert function. Insert and then you have to pass a pair as an argument, a pair of the key value and the map value. So you can do it like this, mp1 dot insert and then some key value like 8, comma 24. So what this does is it inserts a key value 8 and 24. So basically like 8 is mapped to 24 now. MP1 of 8 is equal to 24. And another way to insert elements into a map is like the how you do it in an array. So you can just pass the key value here with the map name, and inside the square brackets you can pass the key value and you can assign it to a mapped value. So this function can be written in the using the insert function like this. So basically like this on line 192 is the same as this statement on line 191. It does the same thing. You can either use the insert function and pass the key value and the mapped value as a pair, or you can assign it directly like this. It's the same thing. So I've inserted three pairs of keys and the mapped values 8, 24, 2, 5, and 7, 1. And another thing to note here for maps is that even if a key value does not exist, you can directly perform operations on that, like what I've done here, MP1 of 3 plus plus. There is no key value 3 before this, right? But still I can perform MP1 of 3 plus plus, and it takes the default value of that as 0. So after I do MP1 of 3 plus plus, then it'll be as if MP1 of 3 is equal to 1 now. And if I perform another increment operation, now MP1 of 3 is equal to 2. So the default mapped value is taken as 0. And you can directly start performing operations even without inserting that key value beforehand. So let's check the output of MP1 of 3 and MP1 of 2. MP1 of 3 is equal to 2. Yeah, that is what I just explained. It was 0 first, and I've incremented it twice. So that's why it's 2. And MP1 of 2, we have directly inserted using this line, so which is 5. And if you want to check MP1 of 8, which we have inserted using the insert function, we can check it, and it should be 24. Yeah. So this was about the insert function. Also, yeah, as I was mentioning, that the key values in a map are unique and sorted. We can print all the elements again using the range-based for loops and the auto keyword. For auto IT in MP1, IT, this traverses through all the elements of MP1 from the beginning till the end. And since all the elements of a map are stored as a pair of the key value and the mapped value, that's why we have to write it.first and it.second. So this will give us the key value and this will give us the corresponding mapped value. So 2, 5, 3, 2, 7, 1, 8, 24. So all the elements of the map are printed, and it does not matter in which order you have inserted it. It will always be stored in a sorted order. So as you can see here, 2, 3, 7, 8, the key values are unique and are stored in the ascending order. So that is the thing you have to remember about maps. key values are unique and are stored in the ascending order. Let's look at another example where the key values of type string and the mapped values of type int. I've inserted two elements, mp2 of cheese is equal to 1 and mp2 of salsa is equal to 2. I'm just showing that the data types of key value and map value can be of like any data type. It can be string, int, or string, char, or float or double anything. So now I've inserted two elements, and if I want to print mp2 of salsa, it should give 2. mp2 of salsa is equal to 2. And if I again print if I print all the elements present in mp2, it will give cheese 1 and salsa 2. Now another thing here is if I would have inserted salsa before cheese, then also the order will be the same because it stores the key values in ascending order, right? And here the key values are of data type string. So it will store the key values in the lexicographically ascending order. And since C comes before S, it'll still be printed in this order. Yeah, so first I've put salsa is equal to 2 and then cheese is equal to 1. It'll still be cheese 1 and salsa 2 because that's how it's stored in a map. And erase function removes is used to remove an element at the position pointed by the iterator. Okay, erase function is also used for vectors and sets and other containers also. I'll show it here and then for vectors also. So if I want to erase the first element, or yeah, wait, let me show it in vectors itself. So we are back to vectors and I've pushed 8, 10, 15, 9, and 6. So that's 8, 10, 15, 9, and 6. And now if I want to erase an element from the vector, I can just write vec.erase and then I can pass either one argument here or two arguments. If I pass in one argument inside the erase function, then the value at that location will be deleted. And if I pass two values, then all the elements in that range will be deleted. So, and you have to pass an iterator here. So if I pass vec.begin, so what this will do is it will erase the element present at vec.begin, which is the first element of the vector. So if we try this out, so after we have erased this, how you can erase the first element. The popback function removes it from the end, right? So if you want to erase the first element, you can erase it like this. And it has been erased the second time. Or if you want to erase the second element, then you can pass vec.begin plus 1, for example. So now 10 has been erased, which was the second element. So this is how you can erase a single element. And if you want to erase a range of elements, then you can pass another thing. Like if I pass vec.end, then all the elements from vec.begin plus 1 till an element just before vec.end, that means the last element. will be erased. So if I perform this, then from 10 to 6, all of this should be erased. Let's check. Yeah, so now only 8 is being output. So this is how you can use the erase function. And you can use it in a similar way for maps too. So that is about the erase function. And there's again the clear function. Clear function is just used to clear the whole container. So if I write vec.clear, this will just erase all the elements of the present in the vector. So only here all the elements are printed, and then after clearing it, there's nothing printed because the vector is empty. And you can use the clear function again for anything, for a set also, or for a map, anything. It will erase all the elements present in that container. So this was about the clear function. And this I have already mentioned. In maps, the keys are unique and sorted, just like how the values in set are unique and sorted. And just like how there was unordered set, there's also unordered map, which stores the elements not in the sorted order according to the keys. And its time complexity can go from O of 1 to O of n square. That's why it's like not recommended in use, but you can read about it for your own knowledge. And these are some more links which you can go through to learn more in depth about all these STL containers in C++. Now, Mayank could continue from here.
Hello.
Hello, yeah,
Hello.
you're audible. Yeah, you're audible.
Yes, second. So guys, you can ask any doubts you have in STL for now. I'll give you a minute. Mhm. So you have no doubts, right?
You can also write your doubts in the chat if you get them later also.
Yeah, you can write them anytime. Please repeat upper and lower bound.
Upper bound and lower bound. Okay. So the upper bound function in a set returns an element. Wait, should I share my screen again, Mayank?
Yeah, just second. I'm sorry.
Hmm. The screen is visible, right?
Yes, yes, it's visible.
Okay, so here I've created a set, right? And then I've inserted all these elements into the set 4, 8, 3, and then I've printed the set. So these are the values present inside the set. And they are stored in the ascending order. Okay. So this is how they're stored 1, 3, 4, 8, 10, and 12. These are the elements of the set. And now if I use the lower bound function, what lower bound function does is the argument which you pass inside the lower bound function, like here I've passed 6. So what this st dot lower bound of 6 will do is it will point to the first element which is greater than or equal to 6 inside the set, present inside the set. Okay, so the first element which is greater than or equal to 6 in the set, what is it? See, there's 1, 3, 4, 8, 10, and 12. So the first element in the set which is greater than or equal to 6 is 8, right? So that is why this will point to 8. And if I print the value present inside, it's giving 8. So that is how lower bound works. If I had passed 8 here, then the lower bound of 8 would have still would have been 8, because the smallest element, I mean the first element which is greater than or equal to 8 is 8, present in the set. Okay, so again it would have been 8. So that's about lower bound. Like, is lower bound clear? Who was asking? Samit. Is lower bound clear? Okay, lower bound is clear. So now we'll move on to like upper bound. Okay, upper bound is also like lower bound, but in lower bound we were seeing the first element greater than or equal to, right? In upper bound we'll be seeing the first element strictly greater than, not greater than or equal to. So now again, upper bound of 6 will, so upper bound of 6, okay. Upper bound of 6, which is the first element here, which is strictly greater than 6. It is 8, right? So upper bound of 6 will be 8. And if you want to see like upper bound of 3, upper bound of 3. So in this set, which is the first element which is strictly greater than 3? It's 4. 4 is the first element which is strictly greater than 3. So the upper bound of 3 would be 4. And if we try upper bound of 12, if you try upper bound of 12 or 13 or any other number bigger than that, then it should return st.end, because there is no element present in the set which is strictly greater than 12, right? 12 is the biggest number in the set. There is no element greater than 12. So that is why it will print the else. That means like this condition is false. it2 is equal to st.end, and this will be printed. So is that also clear? Upper bound is also clear, right? Ah, okay. Any other doubts from anyone else?
Sanskar, hello.
Yeah, yeah.
There was one more doubt regarding how did you print set in descending order using R begin and R end.
अच्छा, अच्छा.
Could you please check the chat box, please? It
हाँ.
was from Abhavya.
Hmm. How did you print set in descending order using R begin, R end? Uh, Set. Okay, set. I printed the set in descending order using. Actually, wait. For a set, what I did was this is what I did for a set. This is just the syntax which you can add here. Like if you write greater int here, then instead of ascending order, by default it will be stored in the descending order. So by just adding this, and if I remove this again, it will be ascending order. And if you want to know more about like R begin and R end, then that's basically a reverse iterator. I'll explain it using the vector itself. Hmm. So the vector elements from first to last are 8, 10, 15, 9, and 6, right? And what I've done here is I'm running a for loop with auto ptr is equal to vec.rbegin. Rbegin is a function which returns a reverse iterator. Reverse iterator is basically an iterator which, when incremented, it moves from the last element towards the first element, like it moves in the reverse direction. A normal iterator, when incremented, moves from left to right. A reverse iterator moves from right to left. So what I've done here is first I've initialized ptr to vec.rbegin. Rbegin returns a reverse iterator pointing to the last element of the vector. So right now ptr is pointing at 6. Okay, the elements are 8, 8, 10, 15, 9, and 6. The elements in the vector are 8, 10, 15, 9, and 6. So right now ptr is pointing at 6, and it is a reverse iterator. And this is some condition which I'll tell now. And I've incremented ptr here, ptr plus plus in the for loop. So when you increment a reverse ptr, it moves backwards. Okay, it moves in the reverse direction. So after ptr plus plus, it will point to 9, and then again after ptr plus plus, it will point to 15. Then again ptr plus plus 10, and then 8. And I'm doing this until ptr is not equal to vec.rend. Rend is again a reverse iterator which points to a theoretical element just before the first element. So it points like just before it. So when ptr is at 8, and again when we do ptr plus plus, it will become equal to vec.rend, and it will come out of the loop. And at each iteration, we are just printing the value at ptr. So it'll print 6 and then ptr plus plus. It'll come here and then it'll print 9 and then 15, and then it'll stop when it reaches vc.rend. vc.rend is pointing at the first at a place like just before the first element. So that is why it is printed in the reverse order like this. It's clear, right? Who had Abhavya? Were there any other doubts? That's it, right? So, Mayank, you can continue from here.
Yes, okay. Thank you, Sanskar. So, hello everyone. This is Mayank Singh from EC third year, and now I'll be teaching you number theory. Okay. So now you know what are different containers are there in C++. Now let's see what their applications are. How can we use them in different problems? So number theory. Here we mostly study about the operations that we can perform on natural numbers. Right, different types of operations. Let's see what those are. Bitwise operations. First of all, we'll study about bitwise operations. Actually, why do we need, first of all, what are bitwise operators? So there's like decimal number system where we have addition, multiplication, subtraction, and all. So there are similar kind of operations on binary numbers as well, like and, or, XOR. So these are called bitwise operators. Okay. So, but why do we need them actually? Why do we need binary numbers? Because in digital you will be told that there are just two states of a system on and off, so that is why we represent everything in binary. But here, what is the benefit? Because you see, for example, you can represent numbers up to 10 raised to the power 18 in just 60 bits. So that is the power of binary representation, and that is why you will be very frequently using them in competitive programming, right? So this was the benefit of bitwise operations. And one thing I'll tell you about this C++ language about binary, that when you are performing bitwise operations on natural numbers, you do not need to convert those natural numbers into binary. C++ takes care of that, right? So for example, here I have performed this. So C++ will convert that natural number into binary. Then it will perform operation. Then again convert that binary number into natural and then give you the result. Okay. So now let's see. Our first bitwise operator is AND. What does this operator do? It takes two operands and performs AND operation. That means it gives you one when both bits are set. When I say set bits, what does it mean? That means both bits are 1, right? So when both bits are 1, our result will be 1. Otherwise, if any of them is 0, and will return 0. For example, you can see 5 and 6. So binary representation of 5 is 101, and for 6 it is 110. So for only the third bit, if you see, both bits are 1. So in the final result, we have 1 at that bit only, and other bits are 0. And our final result is 4. And similar is for 11 and 13. So this was about bitwise AND. Let's move to bitwise OR operator. So it takes two operands and performs OR over number. What does it do? It checks if any one of the bits of those two operands is 1, it returns 1. It gives 0 only when both bits are 0, right? So here, for example, 5 or 6, if we do, so all the bits except the most significant bit has at least one in that position, right? So we have this final result as 0, 1, 1, 1, and which in a decimal number system is equal to 7. So, and similarly for 11 and 13, we have our result as 50. So let's see. And now there's another bitwise operator called XOR operator. It takes two operations and performs XOR over every bit of two numbers, right? So what it does, it checks if both bits are unequal, right? If both bits are unequal, it returns 1. Otherwise, it gives 0, right? So for 0, 1 and 1, 0, it will give 1. But for 0, 0 and 1, 1, it will return 0, right? So you see 5 XOR 6 is equal to 0, 0, 1, 1, right? Because only in first two positions, bits are different and the result is 3. Okay, and in 11 and 13 similar. So now left shift operator. What it does, it takes two operands, just for example, a number and how many times you want to shift those bits. So it shifts whole bits to the left side. That means if you, let's say, want to shift 0, 1 to left, it will it will append two zeros to the right? So for example, if you see you apply left shift operator on 1, it will shift those two bits. So 0, 1, 0, 0 it will become, and which is equal to 4. And 0, 1, 0 will become 16, right? So this is bitwise left shift operator. It shifts whole number to the left of itself. That means in the right side, some zeros are appended. Similarly, the right shift operator, it does what? It shifts operands towards the right. Okay. That means it appends 0 to the left, and you may think what would happen to the ones if they are shifted? They are just gone. I mean, we don't care about that, right? So 0, 0 and see, if we want to shift 11 to two places, right? So last two ones will be gone, right? So the output will be 2 only. So this is about bitwise right shift operator. So this was all about, you need to know about binary numbers or bitwise operation. So you can solve almost every problem with these number of concepts only. Okay. So for example, let's try to solve this. Find the kth bit of a number. Let's move to Sublime and see if we can do that. So let's take any number. See, if this we have this number, I'm sorry, we have this number in binary, right? What would this be equal to in decimal? So this is equal to, I guess, 19. So binary representation of 19 is 10011. And now we want to find out what its third bit is, for example. So how will you do that? Like, can you think of any method using these operations only? Can we find what would be the third bit of 19? Anyone tell just quickly? Okay, I don't know. So you see, we want this again. So we want what is the kth bit of 19, right? Third bit. So when I say third, we start from 0. This is the 0th bit, and this is first bit, this is second bit, and this is the third bit. We want to find out what this bit is, right? So our answer should be 0, right? So if we take just AND, you know what AND does? AND of C, binary of, we take AND of any bit, that would be equal to B, right? This is right now. So what we try to do for a kth position, we try to take AND of this position, and whatever it returns, we know that would be the result of our problem, like what was the kth bit at this of this number. Okay. So how do we take AND of this bit only? So for here comes the left shift operation. We shift 1. What is the binary representation of 1? It is this. And if we somehow shift this 1 to this third position and make it, sorry, this, we will just take AND of this with this number and we'll have our answer, right? So what we do, we just take AND of our number with left shift 3, right? If this is not equal to 0, then we can say third bit is set, right? And if it is equal to 0, we can say that this bit is 0, right? Third bit is not set. Okay, let's see what the output is. I'm sorry, I should have commented this. I'm sorry. Okay, I'm sorry, I just put the wrong operator. So this is the left shift operator. So we just left shift 1 by 3 positions, and we have this equal to this is equal to this number, right? 0 1 0 0, and we take AND with 1 0 0 1 1, right? So it will just give 0 at this position. And what if we had to find if the bit is set at 4th position? So what we do? We'll just change it to 4 and see the output. I'm sorry. Yeah. 19. I'm writing representation as right now. Oh, okay. You know the output, whatever it is. You just get the concept or not. So if you have any problem, you can tell. I mean, anything. Yes. So no. Okay. Another problem. You have to invert the kth bit. Let's say. What will you do here? Can anyone tell? Okay, let me simplify that problem. So you have, that's a 0, and you have to perform some operation with 1 such that you get this 1 and 1, and you have to perform such some operation which gives you 0. So can you tell me like what operation can this be? I'm sorry, this is, so can anyone tell what this operation can be? Of all, just three operations you have studied, right? So which one of can be used here? XOR. Yeah, great, XOR. Thanks. So yeah, you are right. We can use XOR and left shift it with XOR. So simply we can see out number and XOR. This is the operator that we use for XOR and k minus 1, right? Should be. I'm sorry, k is not defined. So for example, we want to invert the fourth bit. It is equal to 1 left shift 3. Now better. So, yeah, it's working. Fine. So you have to invert this bit, right? We had to invert, let's say, third bit of this number. So we had 19 as 10011, right? So if we just invert third bit, it will become 1001111, and it is equal to 27, right? And we have 19 here. So, and let's say we want to invert second bit only, then output is 23. So it is 1011, which is equal to 23 in binary. So this was it. So do you have doubts here? Anyone? See, you will see any bitwise problem anywhere in competitive programming. These are only operations which will be used, right? So you can do solve every bitwise problem with these operators only. It's just that your logic is important. So let's move on. So modular arithmetic. You know what a modular operator is? It just takes a module it just returns a remainder when any integer is divided by a positive integer. Okay, so this is important that the remainder, the number which you are dividing should be positive. That is only important thing here. And yeah, so if A is, you can write A as Q into B plus R, simple division rule, you know. So here R is the modulus, right? So for example, you divide 11 with 3, you will get 2 as a remainder, because 3 we can write 11 is equal to 9 plus 2. So 2 is the remainder. So this is the modulo operator. It just returns to the remainder and is written by percentage sign. Like for example, you want to find what is the remainder when 5 is divided by 2. You just use a percentage sign, okay, and you will get 2 as output. So this is modulus operator, and it is required because, you know, see, like we sometimes deal with very large numbers which may cause integer overflow, because limit of long is 10 raised to the power 18 only, and sometimes our answers may get beyond that. So that is why we use modulo operations to keep in limit, right? So there are certain properties of modulus. You know, a commutative laws like a plus b modulo n is equal to b plus a modulo n. Why? Because addition is commutative, and you will are effectively getting the same value is what a plus b and b plus a is. So similarly for multiplication, and similarly we have associative laws like a plus b plus c is modulo n is going to be a plus b plus c modulo n, and similarly for multiplication. And distributive laws you have, and identities. Like identities are those numbers which give same result when you add or multiply with them. So additive identity is 0, and multiplicative identity for modulo operator is 1, right? And so there's also additive inverse that exists for every integer. So what is additive inverse of a? That is, we represent it as a minus a. And what it is, like, let's say you have to find the additive inverse of 5 when it is divided by 3. So let's say we divide 5 plus 1 modulo 3 should be equal to 0, right? So 1 is the additive inverse of 5, for example. So this is just the additive inverse. You all must be, this must be easy for you all. Yeah. So, okay, here are some other and more important properties of modulus. Like, you perform addition. Why do we need these? Because sometimes the value may overflow, or it might get outside the range. Before you are taking in modulus, even before that, it may get out of range. So that is why we need to be extra careful in dealing with modulus, and that is why we have these properties. So, for example, you have this modulo a plus b modulo n is going to be a modulo n plus b modulo n and whole modulo n, because a modulo n plus b modulo n can be greater than or equal to n. Like, for example, so some just keep in mind one thing: a modulo n, value of this is always be going to be less than n and greater than or equal to 0. So yes. So what happens if a plus b modulo n? So it might happen that if you take a modulo n plus b modulo n, this value might get past this value n. So that is why we take extra modulo here to just keep that value in range. Okay. And similarly, that is similar for multiplication also. You take modulo of a, b, and then multiply them, and then again take that modulo. So, but in subtraction, it is quite somewhat different, right? Because a minus b modulo n is equal to a modulo n minus b modulo n plus, and why do we need this extra plus n here? Okay, because this value might be negative even if this a minus b is positive. Okay, I'll show you an example here. So let's say 11 minus 8 modulo n. We have to find the value of this, right? So what will happen? This a modulo n, that means 11 modulo n will be 1, and b modulo n, that will be equal to 3. So 1 minus 3, this is negative, right? So to avoid that, we add extra 5. So this will not affect our answer, just we are trying to avoid negative value. So this will be equal to 3. 3 modulo 5 is going to be 3, right? And we can see here it was always going to be 3 modulo 5, which is equal to 3, right? So it does not affect our answer. It just we are trying to avoid negative values. Okay. So now let's see division. So division, that is quite tricky. A divided by b modulo n is a modulo n into modular inverse of b, and their product, and divide then whole modulo n. So what is this inverse of b? How do we calculate this? So we know that simply a divided by b is product of a into 1 by b, right? So this is easy, but how do you get this 1 by b modulo n? So actually that's like whole new different topic on how to calculate this, but I'll tell you the formula. You can study about it, but that's like beyond the scope of this workshop. So 1 by b modulo n, its value will be going to be exponent of b. So like it is equal to b raised to the power n minus 2 whole modulo n, right? You just it's good if you just remember this, And we'll discuss in the next section how to calculate this expo, so don't worry about that. But just remember that 1 by b modulo n is equal to this value, right? This is it is also called multiplicative modulo inverse of b with respect to n, right? So these are some properties of modulo. So anyone having problem? Hmm. Just quickly can tell. I guess no. Okay. Let's move to binary exponentiation, right? So what is binary exponentiation? So it is a technique to compute a number raised to some other power in a fast and efficient manner. Right? It utilizes the fact that any number can be represented as sum of powers of two. So let's see what happens. So here our objective is to calculate a raised to the power n. So this naive approach is going to be, what will you do if you don't know anything about this binary exponentiation? You will simply multiply a n times to itself, and then you will get the result like here shown. We have to calculate 3 raised to the power 7, and we just iterate from 1 to 7 and multiply this a to our result for 7 times, and then we get the result. But do we actually need to perform these many operations? Actually, okay, let's find out. So can we do better? Yeah, definitely we can do better. Let's see an example. 4 raised to the power 20. You know, every number can be represented as binary. So I have just 22 in binary is 10101, right? So that is what is written, and 10101. So in writing them in natural numbers, so it is equal to 4 raised to the power 16 into 4 raised to the power 4 into 4 raised to the power 1. And so we now need to calculate these values only. Like we want these three values, and then if we have these three values, we will get this 4 raised to the power 21. Right. So how do we get this? 4 raised to the power 1, we know that it is 4. Now 4 square. 4 square is square of 4 raised to the power n. 4 raised to the power 1, I'm sorry. And again 4 raised to the power 4 is square of 4 square. And 4 raised to the power 4 is square of 4 raised to the power 4. And similarly 4 raised to the power 16 is square of 4 raised to the power 8. So you see how many operations do we need here? Just 4. From 4 square to 4 raised to the power 16. You see in this method, you had to perform n number of operations. For example, here you had to multiply 421 to get the answer, but you actually need just these 4 operations to get all the values required to get the answer. So why are we wasting so much computation, right? We can always have a better execution time. So this is how we calculate. Okay, let's see here. Okay, see, I'm writing something. If anyone thinks it's wrong or has a confusion, can tell me. If a raised to the power n is equal to a raised to the power n by 2 into a raised to the power n by 2 into a, if n is odd and it is equal to a raised to the power n by 2 into a raised to the power n by 2. If n is even, it's so everyone is okay with it, na? Or do you think anything is wrong here? You can just tell me yes or no. So do you think if anything is wrong here or it's correct? Just quickly, please write yes or no. One thing, if you don't know, n by 2 will give a floor value of the floor value. Like 5 by 2 is going to be equal to 2, and similarly 6 by 2 is going to be 3. Right? So just remember that. And what do you think? No response. Yeah, come on, you can write yes or no. If you do not understand, still you can tell. Yes, yes, okay. So this is right. So this we will use this, right? To calculate exponent. For example, we have to calculate expo of, let's say we calculate 2 raised to the power 10 first. We have, let's write a function expo here. So this function will return integer. It will take integer a and b, right? So what will be the result? First of all, we just get value of a raised to the power n by 2, right? So we get a raised to the power b by 2. And if b is odd, we simply return result into a, right? And otherwise, we will return result into result only, and we do not need a here. So, okay. And one more thing, we need a base condition here. If b is equal to 0, then answer would be 1, because something raised to the power 0 is going to be 1. So this is just simple function to calculate, and let's see the output. So it's 1024. You know 2 raised to the power 10 is 1024. Let's check for some other number. 3 raised to the power 7, for example. 2 and 7, it's correct. You can verify. So this is how our function works. It's a recursive solution. So if anyone having problem understanding that, you can tell. Otherwise, let's see how many operations are required here to get the result. For some exponent b, how many calculations here we need to get the result, right? So in each step we are calculating result of b by 2. So first step we calculate power of b by 2, then we need b by 2, and then we need half of that, b by 2 half, right? So that is going to be b by 4, and then in next step we will need b by 8. So can you tell how many operations are going to be performed here? It is log base to n. These are the maximum number of operations that we will perform in to get exponent of some number a raised to the power b, right? So this is the time complexity of this function. And what was the time complexity of our previous approach? Yes, yeah. So the time complexity of this was O of n, and we have reduced that to O of log of n. So that's quite an improvement, right? Yeah, this is the recursive function to get binary exponentiation. And now let's try to write iterative approach, because iterative approach is always better than recursive solution. So let's try to implement same thing in iterative approach. Let's say we have result, right? And same thing while b is greater than 0. In recursive code also we were just putting the condition that if b is there, we will simply return 1. So here also we are doing the same thing, right? So if b is odd, we can check this in this way as well. So if b is odd, what we'll do, we will multiply a into this, and if otherwise we will just square this a and right shift or just half this, and then we will return the result. This is the iterative approach. It gives the same result which we were getting earlier. We are doing same thing actually, just in a different way. We are not calling this function again and again. Instead, we are doing that in one iteration only, right? So if you see, both functions are logically similar, just they differ in implementation. Right? So let's try to calculate now this NCR value. NCR, you know that combinatorics value, n factorial divided by r factorial into n minus r factorial. So let's try to calculate this. So what would be its value? Let's try to write first, and then we will try to write the code. So n factorial divided by r factorial into n minus r factorial. So it is going to be n factorial into binary inverse of r factorial. We need some modular because factorial values can be very large, right? You know that. For example, 10 factorial is something of order 10 raised to the power 6, if I'm correct. So factorial values can be quite large. So we need a modulo that. Let's say we need this value modulo mod, right? So we calculate inverse of r factorial with respect to this mod, and then we calculate inverse of n minus r factorial with respect to this mod, right? So this is going to be our value, or you can say the answer to this NCR. So how do we, first of all, we need to write a function which will return us a factorial, right? So can, like, you help me writing this function, anyone? Let's write a recursive approach, but you cannot speak, right? So factorial, it returns a factorial of n. If n is equal to 1, we will simply return 1. If n is equal to 1 or n is equal to 0, because factorial of 1 or 0 is 1, right? Otherwise, we will return n into factorial of n minus 1. This function will simply give us the factorial of n. For example, we can check, like, say out factorial of, let's say, 5. Is giving 120. You know, 5 factorial is equal to 120. So let's try now calculate this NCR. So n factorial, we have first value. N factorial is equal to factorial of n. Now we have r factorial, which we need r, and we have n minus r factorial, which is going to be equal to factorial of n minus r. So we will just check for n is equal to 6, r is equal to 4, and we will take our mod as mod is equal to. This is a very famous prime number which we very frequently use in competitive programming to take mod. So you will see that in many questions when you start CP. So here we are also taking this as mod. Now, what we try to do, we have to now implement this inverse function also, right? So I told you earlier, how do we get an inverse function of a value? We take this n, and its value is equal to exponent of n with respect to mod, right? So here our mod is just 10 raised to the power 9 plus 7. So this will just return the inverse value to us, right? So we have now this inverse value, and it's simple. So we can simply see out n factorial into inverse of factorial of r into inverse of factorial of n minus r. This is going to be our NCR. Okay, we do not need to pass this mod. I guess I'm messing up with this long. So I will just convert everything to long, because you see, in when you are dealing with factorials or exponents, you should keep extra care of having long, right? Zero, I don't know. Let's check the value of, first of all. Right. 720. So yeah, it's giving me correct value. R factorial. It's 4 factorial, that is 24. Yeah, that is also correct. So where am I doing wrong? I mean, so that is correct as well. So I guess there's something wrong with this function. So yeah, guys can also help me in debugging. I mean, that is important part of CP. This inverse of this. Why is it giving me 0? And function is working correctly. Just a second. How do I move this? Um, this is inverse function is right. I have written this correctly, right? Let me try to import this.
Mayank, I think we need to use mode in expo function.
But yes, yes. Oh, I'm sorry. I forgot this. Yeah, I messed up with this mod. So now I think it will give us the right value. Again, so here you are performing modular multiplication, right? So you have to take mod here as well. And, again, so now we have the correct output, right? So you see, like mod, you have to be very careful while using mod. You can perform these mistakes and which are difficult to identify. So just with practice, you will get better in this, and you will not make mistake like this. So 64 is 15. You know that. Let's try again. 63. Again, it's 20. You can check it is right. Right. So any confusions? Yeah, I guess you know. Prime numbers. You know about prime numbers, right? You are all are coming from JE. So those numbers which have only two divisors, one and that number itself, those numbers are called primes. So for example, 2, 3, 5, 7 are prime and 4, 6, 8, 9, 10 are not, because 4 has, for example, a divisor 2, which is not 1 and not 4 as well. So that is why 4 is not prime. But why do we give importance to primes? Those are like pretty basic things. So because every natural number that is there can be represented as either a prime or can be factorized as a product of primes that is unique up to their order. So that is why we give so much importance to primes, and you will see like almost most of the number theory problems would require prime numbers in one way or another. So that is why prime numbers are important. And let's see. So how will you check if any number is prime or not? So simple. We have to find any number other than 1 and n and check if it divides n. And if we are successful, we can say that that given number is not prime, right? So how can we do that? We can simply iterate. Can you please explain the changes you made in expo function? Yeah, okay, sure. So yeah, you when you are doing this result and for example this, you have to keep taking mod only because this result might exceed the limit. B is here. What did we take mod here? Here it was equal to 10 raised to the power plus 7 minus 2. So it was equal to 10 raised to the power 9 plus 5. So B was like pretty big number, right? So this value can get very big and it may exceed the value of long. Range of long can be up to something around 10 raised to the power 18, and this might get something bigger than this. So that is why we need to keep taking mod here and here. And this is we are just having the we just dividing this b by 2. Right shift operation does that only. So this is what we are doing, right? We just had taken mod these at these two positions. Okay, or not? Okay, that's great. Now, prime numbers. How would you test if a number is prime? So we just create a Boolean function which will tell us if a given number is prime or not. So we simply iterate till n minus 1 and check if that number divided by I gives 0, that means that number is a divisor of n, right? And we need to return false here. And if we do not find any divisor, then we return true. That means the number is a prime. And one thing, for one, we need to explicitly define this condition that 1 is not a prime, right? So if we check, for example, we know 19 is a prime. And if we print output for this, okay, so we are getting 1. 1 means true. That means 19 is a prime. Again, we are, so can you tell me what is the time complexity of this? Anyone? Just, it's quite simple, right? Okay, it's just O of n. We go of 1 because we are making n minus 2 operations, and that is, we write that O of n only. So this, the time complexity of this is O of n. But we can definitely make it better. We do not need these much operations. I'll show you how. Let's write first. Try to write divisors of 60. For example, we take a number. So what are the divisor pairs of? So 1 cross 60 will give you 60. Then 2 into 30 will give you 60, and 3 into 20, 4 into 15, 5 into 12. 6 into 10, and after that you will have repeating divisors like 10 into 6 and so on. So there's one thing common in each and every pair, right? What is that? One of the divisors is always less than or equal to square root of 60, and another one is always greater than or equal to square root of 60. That is quite intuitive as well, right? If both, for example, if both divisors are greater than or greater than 60, then the overall product will also be greater than 60 now. And similarly, if both are less than square root of 60, then overall product would be less than 60. So we need one divisor at least one divisor which is less than or equal to square root of 60 and one divisor which is greater than or equal to square root of 60, right? So, we can use this fact to modify our function and give us a better time complexity. So if I make just a very small change, this, right? So our function will still work in this case. And it will give the same output, 1 for 19. For, let's say, we check for some other number, 40. It is 0. Why this function works? Because if we were to find any divisor of n, we would have found it in this range only, right? Because we saw here at least one divisor has to be less than or equal to square root of n, and one has to be greater than or equal to. So if we find any of these such divisors in this range, only then we can say that the number will have any divisors other than 1 or n. So that is why we just need to iterate through this range only, and we do not need to cover the whole up to n minus 1, right? So that is why it works, and it brings down the time complexity to O of square root of n, right? So this is why how much we have improved with just small change, right? So this is about improve, right? Summarization of n, great. So this was a better approach to find prime numbers. Now, see, okay, can we use this to find all the, let's say we want to write all the prime factors of a number. How can we do that? Let's try to see. So let's create a vector which will store the prime factors, or we can just simply out. We have, let's say, number 60, for example, we take, prime factorization of 60 is 2 square into 3 into 5, right? So this is the prime factorization of 60, and we need to find this. How can we do that? Now we know that every divisor would lie in the range square root from 1 to square root of 60. So we just need to iterate till there only, right? And check if this number currently divides this. We will remove all the occurrences of this number from its representation, its prime factorization. For example, we are at 2 and 2 divides 60, right? So we will remove all 2 square from n, right? So let's say so while and percentage I is equal to 0, we will keep on dividing I from this, right? And we can simply, and if still n is not equal to n, that means we haven't covered all the prime divisors of this. So that simply means one thing, that n is still, and whatever remaining, it is still prime, right? So let's see what is output. So it is 2, 3, and 5, you can see. So that is how we can get all the prime divisors of any number. And if you want complete divisors, or what this exponent is, you can use this a count variable and count how many times it divides the number, and simply you can put this. So it's see, 2 square and 3 raised to the power 1 and 5 raised to the power n is the binary representation of 60. Let's check for another number as well. So 100 is 2 square into 5 square, you know that, right? So this is the prime representation of 100. So yeah, so it's okay now. Anyone having doubts? So let's move on to Sieve of Eratosthenes. So let's say you have to find all the prime numbers in a given range. For example, you have to find all the prime numbers which are less than or equal to n. What would you do? So the naive approach would be to iterate to all the numbers. Like let's say we want all the numbers till 1000 which are prime. So we will iterate to 1000 and check if is prime I. If this number is prime, we will just simply print I, right? So it will give us all the numbers which are less than or equal to 1000 and are prime. But can you tell me what is the time complexity of this? Anyone? Okay. No. So it's 1000. We are making iteration up to 1000, and for each value, we are having a square root of that I computation. So the time complexity for this is going to be n into square root of n for any n. But we don't need this many operations. We can do that in a much better way. Let's see how. So let's first create a vector which will mark which numbers are prime and which are not. So vector, we will create a Boolean array and marking is prime. We have already a function in prime, so we will of let's say 1001 size. And initially we mark every value as true because we are assuming that every number is a prime as of now. And let's mark one as false because we know one is neither prime nor composite. So now we try to iterate on. Let's see how this algorithm works first. So initially all the numbers marked 1 except 1 are marked prime except 1. See, that is what I've done here. So I have marked everyone as true. You can, so this is a property of vector. You can assign every number same value by this method. So I marked everyone true. And then we iterate through every number. Let's see, this is this diagram which will explain you better. So we come to 2, right? If and 2 is not has not been marked yet, so that means 2 is prime, and then we will mark all the numbers which are multiples of 2 as not prime because 2 is a divisor of them, so those are definitely non-prime. So all the divisors of 2 like multiples of 2 like 4, 6, uh, and 8 up to till up to 60. In this example we have used number 60 only. So till up to 60 we will mark every multiple of 2 as false, or you can say not prime, and then we will move on to 3. So 3 has still not been marked, so that means 3 is prime, and then we again will mark all the multiples of 3 as not primes. Then we will go to 4. We see 4 has already been marked by 2, so that means 4 is not a prime. We will move again to 5. 5 has not been marked by any of the numbers, so we will mark 5 as prime, and then we will mark all the multiples of 5 as not primes, right? And then we will keep on iterating this. We'll keep on repeating this process till n, right? So let's implement this. So if the you see if this number has already been marked, right, false, then we do not need to enter into this loop. We will enter into this loop only if it has not been marked or it is prime. So if it is prime, so for all its multiples which will start from 2 into I and which are less than or equal to 1000, we need to increment this by I, right? We will mark them as not primes. And in this way, you can here print out. We know that if we have come here, that means I must be a prime. So you see, all these numbers are prime that we have got less than or equal to 100, right? 2, 3, 5, 7, 11, 13. All these numbers are prime, and these are the only prime numbers less than or equal to 1000 that we have just printed, right? So this was the code. That the same thing which I've written here. So let's see the time complexity of this approach. It requires actually a lot of mathematical calculation, but it comes out to be log of n into n, right? So time complexity of Sieve, and this value is generally very small, so we sometimes write this as O of n only. Right? So this is the complexity, and now we can make many optimizations to this Sieve as well. For example, we again, like we discussed, we do not need to iterate till 1000 here because all the divisors are we will found in till square root of 1 only, right? So if again I print here, uh, if prime, this will still give us the same result. So these are like small optimizations that we can make. Again, one more thing, we can, instead of 2i, we can start iterating from I square. Why? Because again, then also we will receive the same result, because for let's say for all devices from 2i to uh, 3 into I, so till I minus 1 I. So all these numbers 2, 3 till I minus 1, these must have been marked by some any smaller prime, and the smallest prime which hasn't been marked and is a multiple of I would be I into I only, right? So these all would have been previously marked with and some numbers, right? So this is why we can make this, and then there are other different things like uh, segmented sieves which you can study. I'll tell you one website. So this website here, you can find more things about these. Actually, I find this website very interesting, and you can look here for that. Right. So this was about Sieve of Eratosthenes. It tells us what primes. It tells us all the prime numbers which are in a range from 1 to some number n, and it works for numbers as large as 10 raised to the power 7. So yeah, and this is possibly one of the best approaches to get all the primes. This was now we move on to binary search. It is also called half search because you will see why. So binary search. Binary search is a smart searching algorithm. It which only works on a sorted piece of data. That is important, you know. For a binary search to work, the data should be sorted in ascending or descending order. That and it works on the principle of divide and conquer. So that means it will divide data into two pieces and will check for each piece separate in for each part separately as to which one will give us the better result. So that is why it works on the principle of divide and conquer. And also it works in the logarithmic time. Like for linear search to work, let's say you have to search an number in an array. What is the naive approach? You will just iterate through every number and find if the element to be searched is there or not. So that can, in worst case, take O of n time complexity, right? So, but binary search does this in O of log n, provided that the values have to be sorted, right? So this is how binary search. So this is the algorithm of binary search. We take the middle element of the array and for example, we have to search an element in an array, right? And that is sorted in increasing order. So what we do, we take the middle element of the array and compare it with the value which we are trying to search. And if this middle value is equal to the value which we are trying to find, then we just quickly stop because we have found that element. Otherwise, what we will do, if we will check if the value middle value is greater than the value to be searched, then we will limit our search to the left half only. Why? Because middle value is greater than the value to be searched. That means all the values which are smaller than middle value are must be in left side of the middle element. So that is why we restrict ourselves to the left half only, because we know we will find if there is any chance of finding that element, it's in the left half only. And similarly, if middle value is greater than that value, we search in right half only. Right. So this is okay. Let's see an algorithm if you have confusion. So we uh, just define a vector and enter some values randomly in increasing order, right? So this is a sorted array, you can see. And let's say we have to find the index of 17 in this array. So what we will do, we will keep a value, we call it generally low as 0 and high as p dot size minus 1. So low way is pointing to this 1 and high is pointing to this 25. Uh, right. So this is the range in which we are searching initially. So from 1 to 25, we are searching if there is any element which is equal to 17, right? And now, as long as we have this condition true, we will get this middle value, which is, right, we will take this middle value, and if this middle value is equal to our key value which we are searching, we will simply print the index and break out from this loop. Otherwise, if this mid value is greater than this key value, what we'll do? We will search in the left half. So we will see, let's say if this 10 comes out to be the middle value, and we are searching for 6. So we will, what will we do? We will restrict ourselves to this half only, because we know 10 is greater than 6, and the only chance of getting 6 in this array would be in this half only. So we will, what do we do? We will change our high value to mid minus 1, right? So if 10 was greater than 6, we would search till here only, right? So that is why. Otherwise, what we will do, if this value is greater than, for example, in this case 17, and we find 10 as the middle value, for example, then what we will do? We will search in this 70 to 25 only. So what this low pointer will move to the next value just next to mid. So low will be equal to mid. And if we come out outside and without finding the element, then we will simply uh, element not found, because let's see 7, we are getting 7 as output. Let's see what is the index of 17. 0, 1, 2, 3, 4, 5, 6, 7. Yeah. So 7 is the index of 17, and we are getting index of 7 as the output. Let's try to search for 18. And we can see 18 is not there in this array, so element not found. We are getting. So this is exactly the code for this. So do you have any questions with that? Or you can tell. Nothing. Okay, I think. Come on, do not think if it's something silly or not. Uh, you can ask anything, right? So I guess no doubt. So this was it from our side. You can still, if you have questions after the workshop as well, you can ask in the group or to any of us. You can DM, right? And we will share you this PPT after this workshop, and also we will give you a set of questions to practice, which are related to these topics, and you can practice. Okay, so this I'll say this one thing: that do not hesitate to ask anything. Ask whatever you think you do not know, because that is only how you will learn. So this was it from our side. This is our team who are working for this event. So it's quite a big team, you can see, right? And so thank you everyone. This was it from our side. Sanskar, you have to say anything?
Oh yeah, that's it. We'll share the slides after this, and if you have any doubts, you can also ask later after this workshop also.